All right. So what we want to go ahead and do here, right, the next step in our rocket building project, okay, is to, we want a rocket that will produce its own gas. In other words, we want a chemical reaction that will produce the gas to pressurize the rocket for us so we can store the rocket more easily. We don't have to store it at high pressure. We can just store some chemicals, okay? Now, to do this, to make this work correctly, what we need to be able to do is we need to be able to have to know how much reactants we need to mix together. Because if we mix too much of our reactants, we produce too much gas, then the rocket would explode, right? It will burst the pressure containment. So what we want to be able to do is we want to be able to convert pressure or volumes of gases and deal with those in terms of chemical reactions. Okay? So, we have all the tools to do this already. The ideal gas law is going to be able to take care of that problem for us. If we know pressure, temperature, and moles, we could calculate volume, or vice versa. We can find moles from those other values. We know how to do that. We've done some practice problems. But there is a way that we can sort of create a shortcut to make this process a little faster. If we go ahead and standardize, work with a standard temperature and pressure, what we call STP, standard temperature and pressure, we can take the ideal gas law and figure out the relationship between volume and moles. The relationship between volume and moles, and then we can use that essentially as like a conversion process. So what we want to say is, what volume does 1 mole of a gas occupy at 0 degrees Celsius and 1 atmosphere of pressure? Okay, that's fundamentally the question we want to answer. So, what we're going to do is we're going to use the ideal gas law and say 1 mole at 0 degrees Celsius and 1 atmosphere of pressure. And we go through, we do the calculation, and we get an answer of 22.4 liters. So this is important to us because what it tells us is that at STP, standard temperature and pressure, 0 degrees Celsius, 1 atmosphere of pressure, 1 mole of a gas occupies a volume of 22.4 liters. Any ideal gas. Any ideal gas. And for our purposes, all gases are ideal until we specifically learn otherwise. So this is a ratio. This is a way that we can convert volume of gases into moles, or moles of gas into volume. Okay? So what we need to do is we need to be able to calculate what volume will be made from a given number of moles. Okay? So we want to take the moles of gas and convert that into volume, because that's typically the easiest way to measure a gas is to measure the volume. It's relatively straightforward to put it in a container and measure the volume of the gas. And we're actually going to do some of that work next week after next. When we come back from Thanksgiving, we'll do a couple of labs. Okay? Next week is Thanksgiving. So when we come back, right? All right, so here's our rocket. This we have a new design for the rocket here. This is a rocket where we can load in the reactants in separate chambers, and then when we press the button, the reactants will mix and produce a gas. There's lots of different reactions we could use to produce gas. One of them would be the reaction of magnesium, this is an alkali metal, with an acid, hydrochloric acid, to produce hydrogen gas. Okay? So what we're going to do is we're going to take a chunk of magnesium, and we're going to mix it. Let's say we have 50 grams of magnesium, and we're going to mix it with excess hydrochloric acid. Excess means more than enough. In other words, what's my limiting reactant? The magnesium is the limiting reactant. Hydrochloric acid will be in excess. We'll have more than enough hydrochloric acid. Okay? And so what we're going to do is that basically we're going to open up the rocket, and we're going to put the hydrochloric acid in, and we're going to put the magnesium in, and then we're going to close it back up. Okay? And then when we set it off, those things will react and they'll produce gas. The question is, how much gas will be produced? What volume of gas at STP, 1 atmosphere, 0 degrees Celsius, will be produced? So we start like this, like we would start any stoichiometry problem. Start with the limiting reactant, 50 grams of magnesium. I want to convert the magnesium into what? I have grams. I need to convert it into moles. Because what I want to do is I want to go from moles of magnesium to moles of hydrogen. I want to use the mole ratio from the balanced chemical equation. So magnesium has a molar mass of 24.3 grams. Where did I get this number? The periodic table of elements, right? That's how we convert. This is the grams to moles. That mass, the value from the periodic table, gives you the number of grams in 1 mole. So I now have moles of magnesium. The next step in stoichiometry is to convert from what you know to what you're trying to find. So I'm going to convert from moles of magnesium to moles of hydrogen. This is all stuff we have done before. Okay, there's nothing here that is new, nothing here that should be terribly surprising. Okay? The last step is the new bit. Because the problem that I'm asking you is what volume of hydrogen will be produced. So I want to do another conversion, but this conversion is to convert the moles of hydrogen into liters. What is the ratio, what is the conversion when I'm at STP? 22.4 liters for every 1 mole. If you're at STP, standard temperature and pressure, 1 atmosphere and 0 degrees Celsius, for any gas, for any ideal gas, that will be true. Now, what if we're not at STP? How could I calculate this if I'm not at STP? What equation relates moles, pressure, and temperature to volume? PV equals nRT. If you're not at STP, you solve for the moles of hydrogen, take it, substitute it into PV equals nRT, solve for volume that way. This is simply doing that same thing, just fast, because we've pre-solved it. We've pre-solved the ratio of 1 mole of gas at 0 degrees Celsius and 1 atmosphere pressure. Okay? So, we can go through here, we can calculate this, we can find out that when we press the button and the rocket launches off, we get 46.1 liters of hydrogen produced. This is stoichiometry with gases. This is, if you're at STP, you can use this trick. If you're not at STP, you solve for moles and use the ideal gas law, PV equals nRT. Yeah. Solve for moles of hydrogen. So drop this stuff off, put the equal sign here. That'll give you moles of hydrogen. And then they'll give you a temperature and a pressure. And you just solve for moles. Then you could go through and plug those 3 into PV equals nRT. You know R, it's always the same. And solve for V. And yeah, they'll tell you what the conditions are. And sometimes they'll say at STP, and sometimes they'll say at 0 degrees Celsius and 1 atmosphere of pressure. That was what it was set back in the day, whenever somebody decided to set this up.
I'm confused about using PV equals nRT.
Mm-hmm.
Because you're only solving for the moles of gas, right?
Right.
So if in an equation,
You're plugging in, this would give you the moles of hydrogen. The question is, what volume of hydrogen was produced?
so yeah, if you wanted to solve that question, okay, if they give you, it wasn't at STP.
Okay, not at STP.
Temperature and pressure.
We know the pressure, we know the temperature.
And we just plug that in, and then the N would be the moles of hydrogen.
The N would be, calculate the moles of hydrogen,
So you
plug it in with P and T, and solve for V.
And that'll be the volume.
The volume of hydrogen gas.
Okay.
We haven't done anything with mixtures of gases yet.
Oh, yeah, that's
We'll do that on Monday. That's Monday.
So that would give us the volume of the final answer, or would that give us the conversion?
That will give you the volume of the final answer.
Okay.
You could always calculate what the conversion is by plugging in 1 mole. All we did was plug in 1 mole of hydrogen and 1 atmosphere and 0 degrees Celsius. That's where this 22.4 came from. Okay? Now, hydrogen, probably not the best gas you want to use in this kind of rocket, Hydrogen is pretty flammable. We've all seen that. I've demonstrated that in class. Okay? So if your rocket is leaking hydrogen and there's any sort of ignition source, you're going to have problems. Okay? And this guy is clearly having a bad day. So there are other reactions we might use. What's another reaction that we could use to produce gas? Yeah, baking soda and vinegar, right? Baking soda and vinegar is a great reaction. You've all probably done it at home. You've certainly seen the little volcanoes that you can make where you do this in elementary school or whatever. So let's say we wanted to do this in a similar sort of rocket. We'd have to redesign it a little bit. But we want to do this, and we want to use baking soda and vinegar. Okay? Ethanoic acid and sodium hydrogen carbonate reacting. Okay? So the question there is, in this rocket, we need to generate 45 liters of carbon dioxide at STP. So I want the volume of carbon dioxide to be 45 liters. And I'm going to use 5 molar vinegar and some mass of baking soda. Your question, your example problem right now, is based on 45 liters of carbon dioxide produced. What mass of baking soda do you need? What volume of vinegar do you need? So fundamentally, this is a question from last unit. This is a question from last unit. You're doing stoichiometry, right?
Hydrogen carbonate will react with ethanoic acid to form H2O and CO2.
Exactly right. So, what's your first step in a stoichiometry problem? Write the balanced chemical equation. Okay, write the balanced chemical equation. Turn these words into chemical formulas. You should know what the reactants are going to be. Hydrogen carbonate, baking soda, or carbonates react with acids to produce water and carbon dioxide. So write yourself a balanced chemical equation. Start with the carbon dioxide. You're going to have to convert to moles. Figure out how many moles of baking soda, then convert to grams. Figure out how many moles of vinegar, then use the molarity to calculate the volume. All right? Acetic acid, ethanoic, same thing. Ethanoic is the most correct. Acetic acid is a slightly older name, still valid, but ethanoic is the most correct answer. Acetate with a hydrogen. All right, do it. All right, do you have this? Just the equation. I'm just going to show the equation. Okay, I don't want people to get stuck on not having the equation. So this should be your balanced chemical equation. Sodium hydrogen carbonate. So sodium hydrogen carbonate. Ethanoic acid, which is like the acetate ion plus a hydrogen. Or you can think of it as eth means 2 carbons. And the oic is this OOH, that's the carboxylic acid group. So the reaction is this hydrogen reacting with the hydrogen carbonate to produce the water and the carbon dioxide. The sodium and the acetate stick together. Okay? So this is your balanced chemical equation. Coefficients of 1 across the board.
Volume equals moles over molarity.
So molarity is equal to moles over volume. So volume equals moles over molarity. What's the next step? What's the next thing you should be working on? What's the next thing to do?
Convert the 45 liters into moles.
You want to convert the 45 liters into moles. That's a good thing to do. Because you need the moles of carbon dioxide. That's what you have. This is what you're going to start with, moles of carbon dioxide. And you're going to use the moles of carbon dioxide to solve for moles, then grams of baking soda. And then use the moles of carbon dioxide to solve for moles, then volume of ethanoic acid vinegar solution. You need this. That's how you're going to find the volume. Because this is not a gas. This is a solution. This is not a PV equals nRT issue. This is a solution. PV equal nRT is only for gases. solutions, you need the molarity is equal to moles over volume. I don't want to go to grams. I don't want to go to grams. I want liters of carbon dioxide into moles of carbon dioxide. What conditions am I at? At STP. How can you convert from liters to moles? What's the ratio at STP? Yep. All right. So we need to keep going. So let's walk through this a little bit. Okay? Step one, we were going to find the moles of carbon dioxide. 45 liters, 1 mole, 22.4 liters, right? That's what I just taught you. This is the new stuff. This is the only new stuff for this problem, really. Okay? So, 45 liters of carbon dioxide, that's how much carbon dioxide we want to make. That was the information, that's the key piece of information to move forward with. That means that we have 2.01 moles of carbon dioxide. That's how much we want to make. Okay, 2.01 moles. Now, the question is, to make 2.01 moles of carbon dioxide, how much of the baking soda do I need? So I'm going to start with 2.01 moles of carbon dioxide. I know it's a 1-to-1 ratio. This is the mole ratio step from the balanced chemical equation. This is where I convert and say, hey, for every 1 carbon dioxide I make, I need 1 baking soda. I didn't have to do any gram messing around here because this was a gas which I had volume. I did the conversion to get into moles. Now I'm using the moles to convert from moles of carbon dioxide to moles of baking soda. Then I can use the molar mass from the periodic table to convert from moles of baking soda into grams of baking soda. And I find out I need 169 grams of baking soda. Now the next step is very similar. Okay? Couple of ways that you can think about doing it. You can solve for moles of ethanoic acid and then plug into the molarity equation. Or you can use the molarity equation to tell you 1 liter has 5 moles. You can use that as a ratio too. So you can set this step up and say, hey, I know that I need 2.01 moles of carbon dioxide. That's how much the problem tells me I'm trying to make. I know for every 1 carbon dioxide I need 1 ethanoic acid, right? I know that it takes 5 moles of ethanoic acid is what's in 1 liter of solution. 5 molar solution. Molarity of 5 is 5 moles per 1 liter. That's what it means. 5 moles per 1 liter. So I need 0.402 liters of acid. Okay? So to make this rocket work, I would need to mix 0.402 liters of ethanoic acid with 169 grams of baking soda. That would produce the volume that we could calculate to give us the right volume of gas to launch this rocket. Okay? So, what is the new part of this? This is all stuff you've done before. This is all stuff from last unit. I know that it's still sinking in. Okay, that's why we're going to see them a few more times. This is the new piece that we've added today. I can convert from liters to moles. I convert from moles to liters for gases. Notice I didn't try and do this as a gas. It's not a gas. It's a solution. It's an aqueous solution. It's in water. I can't use the gas laws to deal with that. Gas laws deal with things that are in the gas phase. All right, one last little piece we want to tack on here just before we run out of time. Okay? What we want to be aware of is that it's not always the case that the reaction produces what we think it produces. We want to be able to calculate. We want to be able to figure out a gas. We want to be able to do some determinations around it. If you think back to when we were doing empirical molecular formula work, and I said that there were ways we can calculate the molar mass of a substance without knowing what it is, I'm about to show you one way to do that. Okay? So we can calculate the molar mass from a gas density. Let's say we have a baking soda vinegar reaction. Let's say we're making the largest baking soda vinegar volcano in the world. Okay? In the courtyard at a community college. So there's our baking soda vinegar reaction. We're pretty sure that that baking soda vinegar reaction should be kicking out carbon dioxide. How can we make sure? If we can measure the density of the gas, 10.3 grams per liter, and there are ways that we can do this, measure the density of a gas, we can go ahead and calculate the molar mass of that gas, as long as we know the pressure and the temperature. So what we're going to do is we're going to imagine, right, I know that moles is equal to mass divided by molar mass. Take the grams divided by the molar mass, that will give you the moles. And I know that PV equals nRT has moles in it. I can substitute, right? I can take those n's and I can substitute mass divided by molar mass. Now if I just rearrange this, right, if I take and I rearrange this grouping terms, I move the v to the other side there. Mass divided by volume, what is that? Mass divided by volume is density. I can rearrange this. Let's solve for molar mass. Hey, look, I have an equation that says, hey, if you know the density of a gas and the temperature and pressure, you can solve for the molar mass.
This is a capital R stand?
R is our universal gas constant. That's capital R is our universal gas constant, right? PV equals nRT. So, molar mass is equal to dRT over P. Molar mass is equal to dRT over P. Molar mass is equal to dirt over P. dRT over P. Dirt P. Okay? So, this equation is not on the useful equation sheet. The two equations we used to make it were. So the two equations we used to create this are on there. This equation itself is not there. So if I know the density, the pressure, and the temperature, I can substitute in and solve for the molar mass. Hey, 44 grams. Yay! That is the molar mass.
Wait, so does that mean it is producing CO2?
That would make sense, right? That would confirm carbon dioxide production.
And if that was like 142, it's not actually...
We'd want to say, what the heck is going on there? Somebody mixed something up. Okay? So, I'm going to walk through this one because we don't have a heck of a lot of time, and I want to give you this thing to do. So, here's the first rocket. We did the same sort of analysis. We measured the density, pressure, and temperature. Molar mass is equal to density times RT over P. Okay, 2.02 grams. That makes sense. It was hydrogen. Okay, H2 is hydrogen. So H2 has a molar mass of 2.02. All right, two things. I'm about to put your homework up. I also have this super quick little assignment. This is the common assessment thing for the department. This is extra credit. Okay, extra credit, but I need it back like right away. Like now. And I just handed out, I'm handing out too many. So please bring me back all the extras, okay? Take 5 minutes right now, do that common assessment thing, drop it back, give it back to me. And don't forget to write down your homework.